Demonstration problem. The mass to be lifted by the motor of a pile driver is 1,800 kilograms. What power in kilowatts and horsepower is needed to lift it to a height of 50 meters at a constant velocity of 0.5 meters per second? The givens. The mass to be lifted by the pile is 1,800 kilograms. The height the mass is to be lifted is 50 meters. The velocity in the y direction is a constant 0.5 meters per second. Since the velocity in the y direction is constant, we know by the first law that the total force is zero along the y-axis, or all the y-axis forces are balanced. This also tells us that the acceleration along the y-axis is zero. The unknown is what must be the power of the pile driver's motor to lift this mass a height of 50 meters at a constant 1/2 of a meter per second. The equation or equations, well, power is work or energy divided by time. Work is force times displacement, so we substitute in for that. So we get that the power is the force times the displacement. We want the power by the motor of the pile driver, which exerts a force of F sub P. Power is the force by the pile driver, F sub P, times the displacement divided by the time. We see that the displacement is simply the height, or 50 meters. However, we are not given the force of the pile driver, and we are not given the time. To find F sub P, or the force of the pile driver, we note that Newton's first law applies along the y-axis, since the velocity along the y-axis is constant. If the velocity is constant, then the total force is zero. So we write down F net of y is zero. We go to the force diagram to see what the net force in the y direction consists of. We have upwards the pulling force of the lift, or the pile force, F sub P, that's positive, and downwards we have the magnitude of the weight vector, F sub W. So we write F sub P minus F sub W is zero. Solving for F sub P, we get that F sub P in magnitude is F sub W, the weight force, which is mass times the acceleration of gravity. Substituting in numerically, we get that F sub P, or the pile driver motor's force, is 1,800 kilograms times 9.80 meters per second, which is 17,640 newtons. We now add F sub P is 17,640 newtons to our givens. Now we know that the power of the pile driver's motor is F sub P, which is 17,640 newtons, times the displacement, which is the height of 50 meters, divided by the time. We now need the time. To find the time, we notice that the velocity along the y-axis is constant. So we write down the equation for uniform motion, or constant velocity. Displacement is velocity times time. We substitute in numerically. For displacement, we have the height of 50 meters. For the constant velocity, we have equals 0.5 meters per second times the unknown, which is the time. Solving, algebraically, we get that the time is 50 meters divided by 1/2 of a meter per second, or 100 seconds. We add t is 100 seconds to our list of given quantities. Substituting in numerically to find the power of the pile driver's motor, we get that the power is F sub P times S divided by the time, or F sub P is 17,640 newtons. We substitute that in, times S, which is 50 meters, divided by the time, which is 100 seconds. This gives us 8820 newtons times meters per second. But a joule is a newton times a meter. So this gives us 8820 joules per second, and then a watt is a joule per second. So we have that the power is 8820 watts. To find the power in kilowatts, since kilo means 1,000, we simply move the decimal place 3 places to the right. So the power is 8820 watts, or 8.82 kilowatts. To find the power in horsepower, we note that 1 horsepower is 746 watts to 3 significant figures. So this is simply a unit conversion. So we multiply 8820 watts times 1 horsepower over 746 watts, and we get the power to do this is 11.8 horsepower. In summary, the power required to do this by the pile driver's motor is 8820 watts, or 8.82 kilowatts, or 11.8 horsepower. And they lived happily ever after.